signal at different frequencies. And in this way, essentially, if you just summarize this to an imaging concept, the machine collects the image in the Fourier domain. And these gradient coils that control the changes in the strength of the magnetic field, they essentially control how the frequency domain is traversed. So we have a trajectory, we traverse the frequency domain along this trajectory. And of course, these are physical devices, these are coils. You cannot drive them with infinite amount of current, and they have some in the inductance, you cannot change that current very abruptly. So there are some physical constraints on how this trajectory may look like. It cannot have too sharp turns, it cannot have too strong accelerations, and the speed of traversal also has some constraints. So basically, what we would like to, what we try to do is to look at this imaging model and learn, of course, the image reconstruction. Many people did it before. There are many ways to do to learn image reconstruction from MRI. But basically, what we also added to it is learning the scan trajectory. And again, I'm omitting the details, but what is most important probably is that we actually take into account the physics of the machine, at least to some extent, and these physical constraints are strictly enforced on the trajectory that we learn. So what you see on the left is a typical radial scan with 16 shots. So each shot is a continuous operation of the acquisition machine. The signal decays after some time, so you need to acquire multiple shots. You see each shot takes a slice through the Fourier transform. This is the two-dimensional slice of the image. I will show you afterwards a little extension to the 3D case. So you see this is a radial scan. It's pretty standard in the MR imaging. It's one of the standard protocols for acquisition. What you see on the right is the learned scan that was initialized with the radial scan. So you see these completely crazy trajectories. I assure you that the physical constraints are maintained along these trajectories. So the turns are not too sharp, and the velocity, so I'm not showing you the sample points, the time, the way the time actually goes along these trajectories, but it actually satisfies the machine's constraints. And this is what you see in the reconstructed image domain. So on the left, this is the image of a knee, a joint reconstructed from the regular radial scan. And what you see on the right is the image reconstructed from the crazy trajectory. So this is still emulation. It's still not, we haven't tried it yet on a real machine. This is as close as we can get from raw MRI data. Of course, there are some additional complications that need to be accounted for, but they're pretty standard, like non-uniformities in the magnetic field and some other artifacts that exist in the real world. But you can see that both objectively and subjectively, the image is remarkably better. And just, again, I don't know what can be seen in this image, but I think a more interesting set of tasks is when the final outcome of interest is not an image, but something else, some other task. Like, for example, I would like to segment different tissues, like this brain tumor in this example, and I can learn my acquisition protocol, my trajectories in this case, for this specific task, like what I showed you in depth imaging before in the optical domain. So we also tried solving these more complicated downstream tasks like segmentation. And we actually saw that we can get better performance. The image looks not as nice as it looked with the pure reconstruction training, but it does better segmentation. And actually, when we combine several tasks, we typically get increased performance in all of them. And this is just a visualization of the same trajectory that was learned for 3D imaging, again, a three-dimensional radial scan. We are now working on extending these ideas to diffusion tensor imaging, where the space in which the trajectory can be constructed is more interesting, because there are additional degrees of freedom also in acquiring diffusion tensor or the diffusion propagator of the material of interest. So basically, we are trying to take advantage of learning these trajectories there as well. And one last thing that is not strictly related to imaging that I would like to just very briefly show you. So essentially, in all these active imaging modalities, we've seen that by taking advantage of shaping the illumination or the way the energy is emitted to the scene, actually allows way better control of the imaging process and allows to get much better images or solving better some downstream tasks. So what we try to do is to design a light source. So it's not a classical light source, it's a quantum light source that has some prescribed specific characteristics. So in this particular case, where we tried to design a light source that creates entangled pairs of photons with prescribed second order characteristics. And of course, there are many uses for precisely engineered entangled light in quantum communication and quantum computing. So basically, the way it is typically done is by illuminating a crystal that creates a hologram with some particular pump with a light source, and then the entanglement is created by a process that is called spontaneous parametric down conversion, SPDC. So basically, higher frequency, higher energy photons create entangled pairs of lower frequency. So basically, what we built is a forward model of the pump and in this case, a three-dimensional crystal that creates a hologram. And we learned simultaneously through this forward model, we learned how to pump it and how to shape the crystal in order to get the desired characteristics. So we currently have results on simulation, and we are now working with a group of collaborators to actually show these results in a real experiment. I will stop here, and thank you for your attention.
Thank you very much, Alexander. I think